Yes, I'm happy to talk about pimDB. This talk will explore processing in memory, DBMS-Engines on memories. Now, what drives our research and cluster population? Today's data-intensive systems face ever-growing data sets that result in massive data movement that limit the scalability and performance of such systems. Some of the key problems are low data mortality. The massive data transfers across the whole memory hierarchy result in systems becoming either bandwidth or defensive bound. Data movements not only affect the scalability, but also have a huge impact on energy consumption. Another problem is memories getting older. Over the past 2 decades, we witnessed remarkable improvements in terms of capacity and bandwidth. However, latency only improved by 1.3 times, and it still takes clock cycles before data becomes available. Another problem is that current systems primarily focus on the processor, resulting in data growth, and this approach fails to address the evolving demands of data-intensive systems. One possible solution that emerged is processing in memory, as it provides a paradigm shift of how we execute operations near or close to physical memory. And with PIM, the memory transforms from just passive storage component to now a computational active entity. And this is aligned with the shift towards both data and data-centric architectures. By leveraging PIM, we can reduce the data movement across the critical path up to this view, which significantly reduces off-chip transfers because we can do the operations instantly. Another point is that PIM allows us to explore a much higher degree of parallelism and bandwidth because the operations are performed with data execution. So, one such system was introduced by UPMEM. Now that we already have a good understanding about the architecture in previous talks, I will skip the details. However, I would like to focus on comparing PIM hardware directly with CPU-based systems, and especially in regards of bandwidth. And if you want to move data from MRAM to WRAM, you can utilize efficiently R engines that are capable of transferring 1 gigabyte per second per single DPU and 128 gigabytes per second per DPU. If you compare this with a typical server system with 2-channel gigaflow configuration, you can expect only 4 to 8 gigabytes per second. If you further observe PIM hardware and compare it to CPU-based systems, we observed a much more flexibility in PIM, in addition to the dynamic compatibility that is possible. To give some highlights here, for example, the level of runtime in PIM hardware, we have a much higher, but also more flexible degree of parallelism with the use of GPUs and GPUs aspects compared to the threads that we use in this. Additionally, the PIM cache or WRAM replaces the fixed size L1 and L2 caches we find in traditional CPU-based systems. And the key takeaway here is that it is configurable, so we can decide how much WRAM we want to use for a given operation or part of the operation. Additionally, PIM introduces custom DRAM transfer sizes, opposed to the fixed size cache line transfers we have in CPU-based systems. This means that GPUs have the possibility to do much more efficient data transfers from MRAM to WRAM. Here's an example of how PIM processes database pages. First, we distribute the whole data set across a configurable amount of DPUs. Next, the DPU partitions the database pages that are stored in MRAM across a configurable amount of taskets. And these taskets share WRAM, however, they operate on their own address range. Now each testbed can decide how much data it wants to load from the public into the WRAM, and depending on the operation, it might be best to only load part of the tuple, the whole tuple, or multiple tuples at once. So to conclude, PIM is more flexible, allows for dynamic mobility, and this needs to be leveraged by data layouts and operations for performance as I will demonstrate. A quick word about pimDB. It's a database system built from scratch to target PIM systems. Our goal is to explore the design space of PIM and identify new optimizations and strategies to further improve memory systems. In this work, we primarily compare process-centric and data-centric PIM approaches in terms of scalability and parallelism, cache awareness in different page layouts, and the compute-dependent trade-offs we observe in the Some of the features of pimDB are another memory manager that supports traditional memory settings as well as PIM settings, and it supports multiple page layouts, currently implements the NSM text layout, and operations that currently support are scan selections, projections, aggregations, and optimizations. Furthermore, we designed pimDB to leverage PIM's flexibility by allowing location-based configuration of operations that we want to execute. Now we come to some numbers. First of all, our experiment setup was conducted on a server company system with 47 server CPUs, 8 cores per CPU, which supports the threads, resulting in 32 simultaneous threads. The system had 125 GB of VRAM and was equipped with 20 ABUMPIMP memory bits, resulting up to 2,560 APUs and 160 GB in memory. And our evaluation was performed on the PCH. So I'd like to start with a general experiment where we investigated on scaling and parallelism. Here we execute a scan and stack operation on both page layouts, the NSM layout and the text layout. Here the selection evaluates the selection was 50%, and the PIM utilizes up to 2,496 GPUs, while the CPU utilizes 32 threads. And as you can see, this scales exceptionally well for the parallelizable operation on the partition data. And additionally, we benefit from the large parallelizable workload by the higher parallelism, as the operations can be performed simultaneously and on different parts of the data without any CPU contention. This resulted in performance improvement of 68 times in NSM and 62 times in X. Massive PIM parallelism, compute and bandwidth capabilities can get significant improvements in such workloads. Now to evaluate the performance of a single PIM memory chip up to multiple PIM DIMMs, we reduce data size so it can fit into a single PIM memory chip for 8 GPUs and also execute the scan stack operation. And as we can see, a single GPU is of course slower than a CPU core. However, the system scales much more efficiently than the CPU-based system. If you look here, you can see that the PIM system is able to scale up to 456 GPUs rather linearly or almost linearly. And after that, you can see the increase in performance. This is due to the effect of the computation cost. In this case, we have a rather small data set that's distributed across a rather large number of GPUs. Therefore, it is to be expected that the computation cost starts to be dominated. So in-situ data processing allows an increasing number of EPUs to scale linearly by mitigating CPU resource contention and reducing data handling. Furthermore, we evaluated how passive parallelism affects performance. Therefore, we executed the scan set operation with a varying number of passive used during execution. And additionally, we also vary the demand transfer size and therefore change how much data we load and request from ABUMPIMP to ABUMPIMP before we continue with the processing. And as you can see, it is necessary to partition the workload across the class splits to achieve high utilization. However, if you look here at X, you can see that it saturates at 11, 12 class splits, getting closer to one instruction per cycle, which is also the maximum. Very interesting here is that despite changing the transfer size, the IPC utilization remains the same, which means that the additional data transfers can be efficient. If you look at NSM, you can see depending on the demand transfer size, it utilizes, saturates around 6 to 8 class splits. In this case, you can see that we have a rather lower utilization with 0.6 down to 0.4, which means that we are not using the EPUs very efficiently and we are starting to wait for data transfer. The highlight disputes of the IPC count in facts indicates that we are doing compute bound and why in NSM we are bound. Additionally, we have a trade-off between the number of class splits we want to use and the available WRAM. This is basically sharing WRAM, and if we use an unreasonably high number of class splits, we will reduce the amount of WRAM that is available in visual class. To summarize, task parallelism yields interleaving of data transfers and processing within other clusters, and tuning with the demand transfer sizes and further increase the utilization. If you look closer and compare both page formats, you can see, as you would expect, text reduces data transfers necessary for the scan side operation, resulting in a bad performance in the EPUs as well as the CPU. We can observe the specific compute bandwidth trade-off. Here, NSM is higher bound while X is compute bound. If we look here at the NSM with 35 transfer size, we can see that for the evaluation of a single predicate that we do here in scan and select, reading only the attribute that is required, and therefore using a small demand transfer size results in the best utilization and also the best performance. If we increase the transfer size, we now may increase the read amplification for the data we don't actually need. This results in an increase in the utilization. If we now increase it further to 128 byte, we now load multiple couplets at once, and therefore we have multiple attributes that we need for the scan stack operation. Here the utilization increases, however, reducing this amplification results in less performance. We expect that this activity will influence the design of new tailored data structures and operations and the transition to communication-based operations. So data placement and the mitigation of wait time are essential if we utilize individual testing variables. Now, another important aspect is partitioning and data operation code placement, and this ensures shared multi-site execution and are therefore critical for performance and scalability. To evaluate this, we execute 2 experiments where we, first of all, increase the data set size while also increasing the number of EPUs at constant rate. And you can see here that the pimp system can scale along, but it's still providing constant performance. On the other hand, if we distribute the data set across the whole, across a large number of GPUs, we have the highest bandwidth and compute capabilities, therefore resulting in better performance, as demonstrated here, where we kept the data science constant, however, distribute it across an increasing number of GPUs. So with a suitable data operation role placement, we can get faster performance for parallelizable and size-consuming operations on correct data sets. Additionally, we extend our experiments to more complex operations like aggregations. In this case, we vary the number of attributes to aggregate to increase the compute intensity as well as data transfer intensity. And we also measure the construction cycle here. And if we look at NSM, NSM already transfers multiple attributes with one demand transfer, so NSM will not face increased data transfer cost. However, we have increased computation cost due to the aggregation. And rather interestingly, NSM provides a constant performance with increasing number of attributes. And if you look at the structures and cycles, we can see that the additional compute costs can be very efficiently integrated. Hux, on the other hand, is already compute bound. You cannot believe this additional compute cost, resulting in an degrading performance. However, if you look at the IPC, it remains stable, meaning we can interleave data transfers in this case very efficiently. Additionally, we evaluated two materialization approaches. First of all, a full materialization approach, where we materialize the tuple in pre-allocated NRAM, and a big vector approach, where we, depending on the evaluation, set a bit that encodes the position of the tuple for late materialization and late reuse. And we can see here a similar behavior if we look at the execution time. The bit vector creation can relatively be interleaved in NSM, resulting in no visible overhead, and the full materialization, of course, introduces additional data transfers, materials, the records in NRAM, resulting in an overhead. This one here. Hux, on the other hand, cannot interleave the additional compute cost, therefore, bit materialization is visible in this case. And full materialization is rather expensive in Hux, as we have to deal with multiple link pages that we need to manage, and we have to consider all the different data types to reconstruct the result up before we can write it back into NRAM, resulting in rather poor performance. Despite their differences in performance, you can see that with an increasing number of GPUs, both scale very linear. So BIM processing calls for compute transfer capability, primitives, and calculation balancing. Another very interesting aspect is how do we design and deploy our operations in BIM. This depends heavily on, so do we want to use large generalized kernels that support a lot of functionality, or do we want to have small specialized kernels that need more frequent swapping? And this heavily depends, of course, on how much functionality can we fit into IRAM, and how fast can we actually do the kernel swapping, and how expensive is implementation. And in this case, we measured fast CPU kernel loading times ranging from 3.2 milliseconds for one GPU up to 7.5 milliseconds of 2048 GPUs. And additionally, we measured very low implementation costs ranging from $200 microseconds of 1 GPU and up to 3 seconds of 2048 GPUs. We also looked at binary sizes of our scan stack operation, as well as the more complex virtualization kernel. And as you can see, we have still plenty of instruction memory left to extend our kernels. So often, SPIP architecture is well suited for exploring different execution models in DBMS-Engines. So lessons learned. We have massive parallelism equipped with the implemented haslets, and we have efficient scalability for parallelizable operations to accommodate growing data sets, so constant performance is possible. We have dynamic programmability and more flexibility on how we execute operations. We expect different data structures and operations, and the introduction of location-based configurations. Data placement and mitigation of high rate times are essential, and balancing compute and bandwidth operation is our challenging research. Taslet provides efficient interleaving of data processing and data transfers, and as demonstrated with the ABUMPIMP architecture, is well suited to try out different execution modes and effective translation. Thank you very much.